Hello friends. Welcome to the class. Today we will see the topic, resonance and tuning forks. The word resonance comes from Latin and means to resound, to sound out together with a loud sound. Resonance is a common cause of sound production in musical instruments. Resonance is a special case of the forced vibrations. When the frequency of externally applied periodic forces is equal to the natural frequency of the body, free to vibrate, the body readily begins to vibrate with increased amplitude. This phenomenon is known as resonance. Resonance requires three basic conditions. First condition, an object with a natural frequency. The object can be a mechanical device or an electronic circuit. An object's natural frequency is the frequency it tends to oscillate at when disturbed. The oscillation can be a mechanical vibration, as is the case when the string of a guitar is strummed. In an electronic circuit, the oscillation is a variable voltage or current. An object can have more than one natural frequency. These are called harmonics. Second condition, a forcing function at the same frequency as the natural frequency. In mechanical systems, the forcing function is a variable force. In electronic circuits, it arises from a variable electric field. In either case, the forcing function does work on the object it is applied to. Since work is a form of energy transfer, it causes energy to build up in the object. Third condition, a lack of damping or energy loss. For an object to resonate, mechanical or electrical energy has to build up in the object. Anything which removes these forms of energy tends to interfere with resonance. Damping is a means of removing electrical or mechanical energy by converting it to heat. Now, what is damping? Damping is an influence within or upon an oscillatory system that has the effect of reducing, restricting or preventing its oscillations. In physical systems, damping is produced by processes that dissipate the energy stored in the oscillation. See the examples. Here the tuning fork is vibrating rapidly, but now we attach the damping system at the top. Now, here, we see the speed of vibration gets reduced. Now, we see another example. Consider a body is set to vibrate and it vibrates with a frequency f. It is the natural frequency of vibration of the body. A periodic force of frequency n is applied on the vibrating body. If n equals f, the resonance is carried out and the body starts vibrating with an increased amplitude. In case, if n is greater or less than f but not equal to f, there will be no resonance, and only the forced vibrations of small amplitude will occur. Now, suppose that a tuning fork is mounted on a sound box and set upon the table. And suppose a second tuning fork or sound box system having the same natural frequency, 256 Hz, is placed on the table near the first system. Neither of the tuning forks is vibrating. Suppose the first tuning fork is struck with a rubber mallet and the tines begin vibrating at its natural frequency, 256 Hz. These vibrations set its sound box and the air inside the sound box vibrating at the same natural frequency of 256 Hz. Surrounding their particles are set into vibrational motion at the same natural frequency of 256 Hz and we hear the sound. Then the tines of the tuning fork are grabbed to prevent their vibration and remarkably the sound of 256 Hz is still being heard. Only now the sound is being produced by the second tuning fork, the one which wasn't hit with the mallet. Amazing! The demonstration is often repeated to assure that the same surprising results are observed. They are. What is happening? In this demonstration, one tuning fork forces another tuning fork into vibrational motion at the same natural frequency. The two forks are connected by the surrounding air particles. As the air particles surrounding the first fork and its connected sound box begin vibrating, the pressure waves that it creates begin to impinge at a periodic and regular rate of 256 Hz upon the second tuning fork and its connected sound box. The energy carried by this sound wave through the air is tuned to the frequency of the second tuning fork. Since the incoming sound waves share the same natural frequency as the second tuning fork, the tuning fork easily begins vibrating at its natural frequency. This is an example of resonance, when one object vibrating at the same natural frequency as a second object forces that second object into vibrational motion. The result of resonance is always a large vibration.